This video is going to cover simple harmonic motion, and it's going to be an introduction to the material regarding simple harmonic motion. Before we get too far into it, so simple harmonic motion is a specific case of oscillation, let's just discuss what an oscillation is in general. So oscillation is motion that's periodic. So what do I mean by periodic? I mean when we displace a mass to one side, it wants to return not only to its original position that it was displaced from, past that position, and then return to the position that it was originally displaced back and forth and back and forth. Okay, so if you're having trouble picturing something that isn't oscillating, there's lots of examples that you'll see in your physics questions and in your day-to-day life of things that oscillate. So probably one of the most popular oscillating objects in physics questions is the pendulum. Now a pendulum is an excellent example of something that oscillates, because if I were to take the ball and I were to move it over here on the right, it's going to want to swing back to its original position in the middle, and then it's going to want to swing all the way out past that position out here, and then it's going to want to return back to where we begun. So it's going to swing back and forth like this over and over and over again, and that's why the motion is going to be periodic. Another example of an oscillation that you might see in your physics questions is mass on a spring. So in the mass on a spring example, what you do is you have a mass dangling on a spring, you pull it downward like this, and the spring pulls the mass back up, and then gravity pulls it back down, and it ends up going up and down and up and down in a periodic fashion. The last common example in physics questions of things that oscillate is what's called a U-tube. Okay? So what happens is the liquid on one side of the U-tube over here is higher than the liquid on the other side of the U-tube. So gravity wants to pull down the higher side, and because the higher side goes down, the lower side's going to go up, and it's going to go oscillate back and forth as the two sides of the tube try to come to an equal level. So that's the third type of oscillation that's commonly seen in physics questions. The next thing we need to do to start to understand oscillating motion is just learn a little bit about the vocabulary of oscillating motion. So we're going to apply this vocabulary to the situation of a pendulum. So I'm going to sketch out a pendulum. So I have a pendulum, not moved at all, it's dangling straight down. I can pull this pendulum back and be over here, and I could let the pendulum go and it'd swing through that position and it would swing all the way out to here. Alright, so first thing we need to think about is something called the equilibrium position. The equilibrium position is right here. It's the point at which a mass or a particle that's oscillating is either at rest, meaning it's not actually oscillating, it's just sitting there, or its displacement is zero in its oscillation. So it's the point at which our object's going to oscillate around. So it's always going to return to this position, and at this position it'll have no displacement. It's important to remember that a particle at the equilibrium position is not in the translational equilibrium like we learned in our mechanics unit. If we were to move our particle past, out of this equilibrium position, say maybe our pendulum is swung to this point here, the distance that it's been moved from here to here, it's called displacement. It's usually represented with the letter x. And displacement is how far the particle has been moved from its equilibrium position. So in this case, my displacement would be positive, because I've moved it forward from the equilibrium position. If I were to move backward like this, so my pendulum swung this way backward, my displacement would be negative. When my pendulum is swung as far as it can swing, so this position here, when I'm all the way out as far as it can swing, this is what's called the amplitude. And the amplitude is the maximum displacement that my pendulum bob, or my particle that's oscillating, can have from the equilibrium position. The last thing we need to talk about is in terms of terminology, is the amount of time a oscillation takes. So the amount of time an oscillation takes is called a period, which we, in equations and things, will represent with the letter capital T. Make sure you use capital T so you don't confuse it with time. Alright, so a period is the time taken for an individual particle or a mass to undergo one complete oscillation. So what do we mean by this? So if we were to start our pendulum at this position here, so my time would equal 0 at this position. It's going to swing downward, okay, and it's going to swing upward. At this time, once it's gone all the way from down here to up here, it's gone half of one complete oscillation. So at this point, the time would be equal to half a period. I've swung from down here to up here. On my way back, I'm going to swing down this way and return to my original position. Once I return to my original position, I've completed one period. Okay, so it's the time taken for an individual pendulum or particle or mass to undergo one complete oscillation and return to its original starting position. The other way to describe time period, or to describe the oscillation of this pendulum, is in terms of how often it oscillates. And so how often it oscillates is what's called frequency. We're going to represent frequency in equations with the letter F. Now, frequency is how often something happens, and it's also, importantly, the inverse of our time. So if we think about frequency is equal to 1 over our time period, and this makes sense. So if I wanted to know how often something happens, I'd say, well, every time period. Another important thing about frequency is that it's going to be measured in units called hertz, which are equivalent to a per second.